Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of Energy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the sixth one. This lesson is divided into several parts. Let's start analyzing how fins can help to improve the heat transfer rate in a surface. The term extended surface is commonly used to depict an important special case involving heat transfer by conduction within a solid and heat transfer by convection from the boundaries of the solid. Let us start thinking about why do we need to put fins. Think about an electronic chip with a heatsink on top. This heatsink has several fins. Why? The electrical power consumed by the electronic chip is converted internally into heat. The higher the electrical power consumed, the higher the heat that must be dissipated to maintain the chip at an operative temperature. When the electronic chip increases its temperature due to the internal consumption of electricity, the first phenomenon that appears is free convection with the ambient air. Let us start thinking on how to improve the chip refrigeration. Recall that in a steady state, the electrical power consumed equals the heat dissipated by convection. Using the Newton's law, we can write the surface temperature as function of the other parameters. Decrease the refrigerant temperature can only be done in very specific applications. In general, the coolant is air at room temperature. Let's focus in the convection coefficient. We can see that with forced convection, we can increase the convection coefficient. This can be done by placing a fan that moves the air around the chip. However, the increase of the convection coefficient is limited to a certain value that depends on the velocity of the fluid. Last but not least, we can increase the area. The function of the fins is to increase the contact surface with the fluid. What does the fin design look like? There are many types of fins. In heatsinks to refrigerate electronic chips. Other fins increase the heat transfer surface between a tube and the external fluid, or with the inner fluid. Fin tubes are used in heat exchangers. Like straight fins that go along a heat exchanger. We can find fins in heat engines and in electrical engines. Another application of extended surfaces is to reduce the temperature of the contact surface, like the handle of a coffee cup or a frying pan. What is the physical phenomenon that allows fins to dissipate heat? If the base is hotter than the fluid, there is a flow of heat from the base of the pin to its end, or tip, which is colder. QB is the heat that crosses the fin base per unit of time. Because the base is hotter than the fluid, the cylinder is also hotter than the fluid at any distance from the base. Therefore, the heat coming from the base, by conduction, is transferred by convection to the fluid in the lateral surface. Eventually, the cylinder can also transfer heat at the tip. Therefore, the heat transfer is a combination of two phenomena, the heat conduction through the section of the fin and the convection in the surface of the fin. We call QF to the heat transfer rate from the fin to the fluid by convection. What are the geometrical parameters that define Fn? LF is the fin length. That is, the distance from the base to the tip. PF is the fin perimeter or wetted perimeter. SF is the cross-sectional area. It is the section through which the heat is transferred by conduction from the base of the fin to the tip. AF1 is the surface of one fin. It is the contact area between the fin and the fluid. The fin area can be only the lateral area in contact with the fluid, for instance, for adiabatic tip fins. For convective tip fins, the tip area, which is the cross-sectional area, must be added. Can the diffusion equation be used to calculate the temperature distribution of a fin? A fin is a solid without internal heat generation that we will consider in a steady state and with uniform and constant thermal conductivity. However, its temperature profile is not a straight line. This is because the diffusion equation, which is applicable inside solids, cannot be applied in extended surfaces. The Laplace equation is not applicable because in an extended surface, there is convection with the surrounding fluid in parallel with conduction across the solid. The last question before developing the equations to obtain the temperature distribution is to check the one-dimensional conduction hypothesis. Is that right? Absolutely. Conduction allows heat to go from the base to the tip, and from the axis to the external surface. Therefore, it is needed a difference of temperature between the axis and the surface. However, if this temperature difference is very small, it is reasonable to consider only one value of T for each cross-section. It can be demonstrated that, when the Biot number is very small, the difference of temperature in the cross area is very small compared with the temperature difference between the fin and the surrounding fluid. The Biot number is a dimensionless number defined as the product of the film coefficient multiplied by the volume, which is divided by the product of the thermal conductivity times the outer surface. For a fin, the ratio volume outer area can be replaced for the ratio between the cross-sectional area and the perimeter. As a practical rule, we will consider the one-dimensional conduction hypothesis to be fulfilled if the Biot number is below 0.1.